Hi, this is Group29. I'm Juhi and I'm here with my teammates Vasu and Jiwang to present our paper Smoother, a smooth, renewable, power-aware middleware. The agenda of our presentation is as follows. We'll talk about the background, move on to the introduction, discuss some of the current solutions, their limitations, go to the system design, evaluation, weakness, and then the conclusion. The idea of the paper. So, while glancing the paper, the first thing that pops out is that it's trying to propose a solution to address the challenges of using renewable power in electricity grids and systems. The proposed solution is called Smoother, which consists of two major components called flexible smoothing and active delay, both of which will be discussed in detail in coming slides. So, background of the paper is focused on the challenges that are posed by high electricity bills and the negative impacts caused by the carbon intensive fuels. This highlights the need for energy efficient management, but has also two main challenges, intermittency and fluctuations. Before moving on, let's look at two major concepts that are underlying principles for this paper: power infrastructure and consumption in systems. Let's take an analogy of the human body to understand this concept. So, as we know, that human body is a system that requires energy to function. The food we eat provides the needed energy for our body. Some food are better and some food might not be as healthy as the others. So, in order to optimize our body's energy consumption, we can estimate our body energy by taking into account two factors: resting metabolic rate and energy expenditure during physical activity. Once we have this estimated body energy, we can then look into how we can optimize our energy consumption to make sure that we are fueling our body in the most sustainable way possible. Now, if we translate this analogy into the power infrastructure, the digestive system acts like a power infrastructure. Resting metabolic rate is the power used by machines at idle, which is P idle. Energy expenditure during physical activities is the power used by machines at full capacity, which is P full. So a combination of this can give us an estimation of the power. Now moving on to the second concept. The second concept is wind energy source. This is pretty intuitive. You can just imagine a ceiling fan that is used to generate electricity, for example. So the speed of the spinning blades will be directly proportional to the electricity that is generated. To optimize the electricity, you might want to change the speed of the fan, because if it's too low, then there might not be any electricity generated. And if it's too fast, then there is a risk of the fan breaking down. If we translate this to the wind turbines, then the speed of the wind is on which the output of the wind turbine depends on. If, let's say, the too slow and too fast scenarios happen, that means we have the cut in and cut out speeds that need to be considered to optimize the power coefficient for a wind turbine. Now we talk about the two challenges. So the challenge one is high fluctuation, and it's a major challenge because it leads to instability of both grid and the clusters, which eventually increases the management overhead for renewable energy. Challenge two is low power utilization, which causes an imbalance between supply and demand because renewable power generation and workload power demand may not match. This will result in the underutilization of renewable power in the systems. So we do have some current solutions, but the point of the paper is not to go in detail of these current solutions, but rather look at the limitations of these solutions so that we can propose a new solution. That is the topic of this presentation. So multi-green is a cost minimizing control algorithm, but it has a limitation of overlooking the effects of fluctuation on the grid system stability. Cost minimizing online algorithm looks into storing the renewable powers in the battery, but then it overlooks the fact that doing that will require large battery capacity and higher battery charging discharging rate. iSwitch and workload-based scheduling algorithms also have a similar limitation, which is that they decrease the stability of the cluster. This is why we need Smoother. Now, Smoother, as mentioned before, contains of two main components: flexible smoothing and active delay. Flexible smoothing is nothing but basically optimizing the charging discharging rate via computing the minimum variance of the renewable power supply to the systems. Active delay is nothing but matching the deferrable workloads with generation of renewable power so that we can improve the utilization, which was mentioned as one of the limitations before for one of the current solutions. So this way we can use Smoother and overcome those limitations. Now, looking at the system design, we can divide this power generation region into three regions: region 1, region 2, which is subdivided into region 2.1 and region 2.2. To understand this, let's take the analogy of maybe driving a car on the road. As you drive, the road conditions will change. Sometimes it's bumpy, sometimes it's curvy, sometimes it's straight. And depending on the condition of the road, you might need to change or adjust your driving style. It is very similar to wind power generation. In wind power generation, the speed of the wind varies, which is why the power grid will need to adjust to these fluctuations. Coming to region one, it's pretty straightforward. It's like driving on a very straight road with no bumps, no curves. So if you translate this into the wind power generation, wind supply is relatively stable, so you don't need much adjustments. But if you move on to region two, where the road starts getting curves and bumps, so for region two, one, if let's say the curves and bumps are moderate, then wind power fluctuates moderately, which means we can use batteries to complement this fluctuation, and we can adopt flexible smoothing to provide a relatively stable supply of renewable energy. But now, if the road has extremely high bumps and it's almost impossible to drive on the road, then the power grid would need to carry out much higher battery discharging and charging rate than other regions to maintain the stability. Considering the trade-off between the smoothing effect and the required maximum charging discharging rate, we can conclude that we do not execute flexible smoothing in smoother over here. An important point to note is the concept of energy switching time, which is introduced to represent the impact of wind power fluctuations on the system. This is used to differentiate two main regions, where a smaller region one means that there's a large number of charging discharging operations. So this is basically important because we need to consider the trade-off that is needed between battery consumption and energy switching to understand the overhead in real systems. Moving on to G1 to explain the system design.
Thank you, Juhi. Now I will present the Smoother middleware design. Smoother is connected to both the renewable wind power and the grid power. On the power side, it uses the flexible smoothing protocol to smooth out unstable wind power. On the server side, it uses the active delay protocol so that the servers can use more percentage of renewable power overall. Here we have two graphs that summarize the protocols respectively. Flexible smoothing uses battery packs as a buffer that charge or discharge themselves to smooth out wind power production. But this protocol uses less battery capacity than competition, such as some cost-minimizing online protocols. Active delay basically defers jobs with softer deadlines to execute at times where wind power energy is sufficient. We can see from this graph that the green line is the renewable power generation, and job 2 was originally scheduled here, but it can be moved here, where there's much more renewable power, and renewable power utilization rate will go up. So the first step in flexible smoothing, we need to know the short-term wind power prediction to develop the optimal charging and discharging scheme for the battery packs. The paper mentions a machine learning model, LSS-VM GSA, that can predict short-term wind power pretty accurately. LSS-VM stands for least squares support vector machine. Support vector machine basically maps input data into high-dimensional space by non-linear mapping, a powerful tool for data regression, like a neural network. Least squares means that it uses square errors. It can overcome overfitting problems and achieves enhanced generalization. It trains really fast because it solves a linear system instead of a quadratic programming problem. However, there are still some limitations to it. It is very time-consuming to choose proper kernel functions and parameters. That's where gravitational search algorithm comes in. It is inspired and based on the modeling of the law of gravity and motion. It has very robust performance in optimization problems in high-dimensional space with incomplete mathematical formulation. It has great performance in parameter selections, so that's why it can help choose the optimal kernel functions and parameters in the LSS-VM model. Here I will give an overview of how this model works. We use historical weather data that consists of normalized wind speeds and normalized wind directions to train the LSS-VM model, and then use GSA to accelerate finding the optimal kernel functions and parameters. Then we can just input the current weather input, and it will give us short-term wind power prediction. And now let's look at the accuracy of this model. So in the 48 hours prediction consists of 48 data points. 26 data points are within 5% error, and 47 data points are within 10% error. So that's 98% within 10% error. So that's basically very good. Now we have the accurate short-term wind power prediction. Next step will be to determine if the wind power in a short period is smoothable or not smoothable. The key is to choose a good cutoff point in capacity factor variance. And later I will use its CDF value to represent it. Let me explain a little bit more about this. Capacity factor is the normalized wind power at a particular time. It is the current wind power divided by rated power. Capacity factor variance is the variance of capacity factor in a duration of time. The graph on the right is a cumulative distribution function of capacity variance in order of 10 to the power of 11. The data is from the wind power in California in a month in 2011. We can see that the majority of the variance, capacitor factor variance, is actually quite low. 95% of it is below 2. So it means that most of the time, the wind power is relatively stable, but the 99th percentile, like right here, has a variance over 10. That is when the wind power is in region 2, and it has huge ups and downs, and it goes crazy. Yeah, another thing we can note is that, as we can see from this graph, we need more battery charge and discharge rate, or effectively more battery capacity with increasing CDF values. This is pretty obvious because since more unstable wind power production needs more buffer, but switching times between grid power and renewable power goes down with CDF values because intuitively, since there's more battery capacity, there will be less need to switch to grid power. We want switching times to be low and battery capacity to be low as well. The paper balanced it out by picking the CDF value of 0.95. So flexible smoothing is deployed around 95% of the time. Now let's look at the scenario where we smooth with the wind power and find the optimal charging and discharging scheme of battery packs. The problem can then be transformed to a non-linear programming problem. Each capital letter represents a vector of power values each time slot, say around 5 minutes, during a short-term period, say 1 hour. U represents the raw renewable power vector. S is the battery power vector. Its values are positive if the battery discharges power to the system, and negative if the battery is being charged. A is the smooth overall power supply to the system. Then our goal will be to minimize the variance of power values in vector A. And to solve that problem, the problem place its constraints on battery capacity. So there are 3 constraints on battery capacity. The first one is the overall discharge of the overall cumulative discharge cannot exceed 90% of battery capacity because complete discharge can ruin battery packs rather quickly. The second and third constraints are trivial, namely a single charge cannot exceed the raw power supplied, and the overall charge cannot exceed the capacity of the battery. The battery capacity values affect to a degree how smooth the final power is. The more capacity, the smoother, but it has diminishing returns. The paper picks the value that can sustain maximum discharge rate for 5 minutes. The maximum discharge rate is determined from empirical data at CDF value of 0.95. Now I will move on to discuss active delay, which is a server-side protocol. Server power requirements often mismatch renewable energy production. On the graph, the green dotted line represents the smooth renewable power production, and the brown lines represents the server power demands. We can see that the shaded region represents the wind power that is not being used. Actually, if we look at the server peak here, if we could shift the peak into this region, then we can much better utilize the renewable power. So this is the basic idea of active delay. For servers, they have different job types. They have real time workloads, for example, responding to web access, streaming video to clients, and online shopping transactions. But they also have deferrable jobs, batch jobs, like neural network computation, compilation of a huge project, or map-reduce tasks. Some jobs can therefore be deferred if they have software deadlines until wind power is sufficient and ample. Here, I will give an example and overview of the active delay algorithm. The algorithm maintains two queues, a request queue and priority queue. The request queue is a standard queue and maintains FIFO order. In the request queue, it will calculate the power usage of each job request in the queue and constantly update their slack times. Slack time is defined as the job deadline minus the job runtime minus the current time. Basically, it means the maximum time the job can be deferred before it has to be executed. Each job request will be pushed to a priority queue, and the job with least slack time will be processed first. So here, job 2 has slack time of 6, so it will be processed first. And then it will obtain the available, so the algorithm will obtain the available green power for the next 6 time slots according to the slack time. And it will determine the optimal start time for job 2, which is time 2. We can see from the graph that the job 2 originally scheduled here will be shifted to here to be executed. And then the algorithm will update the available power from time 2 to 4, from 8, originally it was 8, and now it only has 2. And now I will move on the presentation to Vasu for evaluation.
Thanks, Jinwan. Let's start with evaluation. So we are going to evaluate both parts of smoother, the flexible smoothing and active delay. For flexible smoothing, the metric of evaluation is energy switching times. Energy switching times represent the time it takes virtual machine to shift between grid-powered clusters and renewable-powered clusters. The lower this value is, the better. For active delay, the metric of evaluation is renewable power utilization. It represents the amount of wind power utilized to run the servers. The higher the utilization, the better it is. So the author used 3 real workloads to test both of these components of smoother: the Google cluster data, web workloads, and batch workloads. One thing to note is that the CDF value is set to 0.95 for the evaluation purposes by the authors, which means that the region 2.2 will only occur 5% of the time, where we can't use flexible smoothing. Now let's move on to the flexible smoothing. So here you can see that on May 18th, the wind power has high volatility. It's varying too much. And on May 2nd, it's rather smooth. So now if we see the second graph, here we can see that on May 18th, the flexible smoothing is able to reduce the switching time significantly. But now if we see May 2nd, there's not much difference. From this, what we can conclude is that flexible smoothing plays a more important role when there's a lot of variation, but it's not able to provide greater reduction in switching times when the wind power is already smooth. Here the authors compared the energy switching times between battery storage solution and flexible smoothing using 5 different web workloads. Flexible smoothing does this by pre-calculating the battery charge and discharge strategy to provide smooth wind powers to servers. Here you can see that in every single case, flexible smoothing provides lower switching times compared to battery storage solution. So the takeaway from the evaluation of flexible smoothing is that it leads to reduction in switching time significantly compared to other solutions when the wind energy has high volatility. Now let's evaluate active delay. First, let's understand what are all the components in this graph. The blue region indicates the amount of renewable energy supply we have. The green line indicates the amount of renewable energy utilization using just flexible smoothing. The red line indicates the energy utilization using flexible smoothing and active delay. Now, if we look at this region marked by the black line, we can see that the red line is not covering the whole blue shaded part. This means that we have very low energy utilization here. This is because the total supply of renewable energy exceeds our workload supply. So active delay is not able to perform to its very best. But now if we move on to this graph, we can see that the amount of total energy of wind power is low. And here using active delay, we are able to cover most of the wind power generated. So basically, active delay is especially useful when the amount of renewable energy supply is low. The authors also did one more evaluation on active delay. Here they compared the flexible smoothing and flexible smoothing plus active delay on different workloads. We see the same result here. When we have a low renewable power, we can see that using active delay, we have high renewable power utilization. And overall also, we are able to achieve better utilization just compared to flexible smoothing. So the takeaway would be that active delay increases utilization of renewable power regardless of energy output, but it performs the best when renewable power supply is low. The author were also able to get an average increase of 170% in utilization using active delay. Now let's move to the weakness of the paper. So we found three weaknesses in the paper. The first is the dependence on accurate predictions. The machine learning model used to predict the wind power was developed in the original paper to predict in 1 hour intervals. But in this paper, the author used it to predict in time points separated by 5-minute intervals. And this would require like finer selection of hyperparameters to get an accurate prediction of wind power. In the original paper, it was mentioned that it has like an error rate of 5%, and the author in this paper also mentioned that this is an error rate of 5%. So we can't be sure whether it's as accurate as the author indicates. The second weakness is limited evaluation. The evaluation of smoother in the paper is based on simulation than the real world deployments. So we can't say that these evaluations that we saw reflect the actual performance of the system in practice. Third is the limited applicability. Smoother is designed to be used for renewable energy sources that exhibit significant power fluctuations, such as wind or solar. But for other renewable sources, such as hydroelectric or geothermal, which are more consistent, this would not be needed. Now, to conclude, Smoother middleware is a practical and effective approach to address the energy consumption challenges faced by the data centers. It is able to increase the stability of the renewable energy by reducing the frequent fluctuation using flexible smoothing, and it is able to increase the utilization using active delay. But this is on paper. We can't be sure until it is deployed. But if on deployment, if the performance is similar, then we will able to reduce the cost of grid energy consumption and carbon emissions. Thank you.